All right, in chapter 3 and 4, we're going to start looking at higher order differential equations. So notice up to now, all we've had is a single derivative, dy dt, or just a y prime. And in these sections, we're going to start looking at much higher order differential equations. 3.2 just goes up to second order, which we're going to kind of focus on. And actually, it's not just 3.2. All of chapter 3 focuses on second order. All of chapter 4 focuses on higher than 2 orders, so that's an nth order. But the principles and the definitions are all the same, so I'm going to kind of squish them together. So what we're going to do is look at differential equations of this form. So they're of a form where, in this case, these a's, so the a naught, the a1, the a sub n minus 2, the a sub, all of those are constants. So those are numbers. And then the y to the n, the y to the n minus 1, all of those are derivatives. So like this is obviously a second derivative. This is an nth derivative. So we can have much higher order derivatives. Now, chapter 3 or 3.2 starts out, and actually 4.1 does as well. There's two different theorems. I'm just going to write this on the side here so you can look at them. 3.2.1. and theorem 4.1.1. Now, both of these theorems basically state that this type of a differential equation, this one that I have written here, that there is a solution, it's going to be unique, and that it's defined on some interval where everything out in front of these derivatives are continuous. So because all these a's are constants, they're just numbers, then of course they're continuous. So really, we would have to look at this function for continuity to see exactly where these differential equations are going to have unique solutions. All right, but for now we can you can look at those theorems and then understand that we are going to have unique solutions to these type of differential equations. All right, a couple other definitions here. So we're going to say that this differential equation is homogeneous if g of t is equal to 0. So if g of t is not equal to 0, then it is non-homogeneous. Another definition that we need, and this is kind of getting a little bit into some linear algebra, but a definition of linearly independent functions. So we're going to say that y1 of the book looks like it's using t. Okay, so y1 of t, y2 of t, all of these up to yn. So we're going to have n different functions of t. These are linearly independent Now, to me, linearly independent means different. So that's sort of another way that you can think about linearly independent. These functions are different. So like x and 2x, they're not really different functions. I understand there's a constant out in front, but the x's themselves are not different. But here's how we can show this. There's kind of two different ways we can show this or do a definition. So we could say that the linear combination, so linear means line, right? So we're going to put all these functions with numbers out in front of them, so kind of like in a line, plus c sub n, y sub n, whoops, y sub n of t. We're going to set this linear combination of these functions equal to 0. And we are going to say that these functions are linearly independent if you find the constants where they're equal to 0. And the only way to get that is if all those constants are all 0. So if C1 is equal to C2 is equal to Cn is equal to 0, and it's the only way. And the reason that I stress the only way is that if all of these constants are 0, 0, 0, 0, then we've got 0 plus 0 plus 0, which is equal to 0. So zeros always work, but if it's the only thing that works, then it's linearly independent. So you kind of have to search for other constants that would make it 0. And then the other way that we can do this is with a Wronskian, and I'm going to have to define that for you as well. So if the Wronskian is not equal to 0. The Wronskian is really good for 2 or 3 functions. So let me give you let me show you what the Wronskian is here. So let me do a Wronskian for 2 variables, or 2 functions, sorry, y1 and y2. Now the Wronskian is a determinant. You guys have seen determinants before in Calc 2. When you saw cross product, it might have just not been called a determinant. With the functions in the first row and their derivatives in the second, so y1 prime, y2 prime. And so this Wronskian, what you do is you multiply, this is kind of an algorithm for a determinant. You multiply down, then you multiply, I think this is multiplying down, come over here, multiply up, and subtract that multiplication. All right, so it goes y1 times y2 prime minus the other diagonal multiplied together, y1 prime, y2. So that's the Wronskian for 2 functions. The Wronskian for 3 functions, I hope I can fit this in here, this is going to be tricky. Determinant, we've got the 3 functions in the first row, their first derivative in the second row, their second derivative in the third row, now when you guys have done this before with a cross product. So with a cross product, you normally had I in that upper left-hand corner. Now we have a function y1. Then what you do is ignore the first row and first column. You just ignore those. And what you're left with is this block on the lower right, and you find the determinant of that. So that is y2 prime, y3 double prime, minus y2 double prime, y3 prime. Now in finding this determinant, the signs change. I don't know if you remember this from cross product, but it was positive I and then minus j. So, but in this case we don't have a j, we have a y2. Times, we ignore that row and column that y2 was in, and that leaves us with these things kind of on these 4 things on the outer part. And we find the determinant of those. So that's y1 prime, y3 double prime, minus y1 double prime, y3 prime. And then one more here, we've got y3. And then we ignore that row and column and find the determinant of the 4 on the lower left, which is y1 prime, y2 double prime, minus y1 double prime, y2 prime. All right, so those are the Wronskians. So you can find the Wronskian. If you don't get 0, then the functions are linearly independent. All right, now I need to tell you what all of this is about, all these definitions. Okay, so we're still looking at differential equations. So we're looking at them like the a naught y to the n plus a1 y to the n minus 1, etc., all the way until we get down to a sub n minus 1 y prime plus a naught y. Now, if this is equal to 0, so we're looking at the homogeneous differential equation here, then solution to this differential equation is going to be, and this is called principle of superposition. So the solution is going to be some y of t is equal to some constant times y1 of t plus c2 times y2 of t plus all the way until we hit a c sub n y sub n of t. So what I want you to notice here is that we have an nth derivative and we have n functions for solutions to that differential equation. Now this is the solution if two things happen. One, y1, y2, all of these y's are solutions. Are solutions to, I'll call this equation up here star. All of those are solutions to that equation star. They all have to be solutions, and they all need to be linearly independent. So they all need to be solutions, and all of these functions are linearly independent. All right, the next sections of this chapter are going to be all about finding those y's. How do we find those y's? And then once we have them, now we know how to put them together. We put C1, C2, we put constants like that out in front, and we add all those together. Right, so this is called principle of superposition. So superposition says add all those functions together with constants out in front. And then one other kind of definition that we need here is that if this is true, if, oops, what did I want? Oh gosh, I didn't want to do that. Okay. If, here we go, y1, y2, yn, if those are solutions, and if all of those functions are linearly independent, then we say that y1, y2, up to yn, that this is the fundamental set of solutions. Okay, that's the fundamental set of solutions. So now, what if it's non-homogeneous? It's kind of the next question to this. So if it's non-homogeneous, then this would be some g of t in there. And that g of t can be comprised of different solutions. So if that is true, then what happens here is that you get a whole other set of functions here. And we can call this, let's call this y sub p, because these are called the particular parts, plus, I don't know, there could be a bunch of them, y sub pk. So I'm saying that this is this y sub p1, it's a particular solution and it's the first one. And then we could have a bunch of them. So we could have k of them. So this is true, and the solution to it is going to be all of these things, the fundamental set with constants out in front, plus the particular solutions, notice there's no constants out in front there, all added together. Now these y sub n's, those have to be solutions to that initial homogeneous differential equations. They have to be linearly independent, and then the other thing that needs to happen is that this y sub p1 through y sub pk are solutions to the non-homogeneous differential equation. So once the g's are back in there, those are solutions to the non-homogeneous differential equation. All right, a couple different examples. We're going to do one of, or two with linearly independent, and then we'll do one with kind of how to put these solutions together. So the first example, and I'm going to make these pretty simple, is y1 of t, which is equal to 2t plus 3, and y2 equal to t squared, linearly independent. So remember that there are two different ways. The first way was to take constants, put the functions multiplied by those constants, set that equal to 0, and see if you can find the constants that are not 0 where this will work out. So what I would do is gather all my t squareds together. So we've got a c2t squared, plus I'd gather all my t's together, 2c1t, and I'd gather everything else together and set it equal to 0. Now the only way for this to equal 0 is if everything out in front of t squared equals 0, everything out in front of t equals 0, and everything out in front of out in front of nothing, t the 0, equals 0. And I shouldn't have said nothing there, maybe out in front of 1. So if we look at everything out in front of t squared, well, that gives us a c2, and that has to equal 0. And then everything out in front of t, that's 2c1, and so c1 has to equal 0. And if you look at even this other part of it, where we've got 3c1, that also has to equal 0, and so c1 is 0. So really the only way that we got this is where all of those constants are 0. So check, that makes it linearly independent. The other way we could do this is with the Wronskian, and for the Wronskian you put the functions in the top row, their derivatives in the second row, so the derivative of 2t plus 3 is 2, the derivative of t squared is 2t, then you find the determinant, so that's 2t plus 3 times 2t minus 2t squared. And hopefully it's obvious to you, even by looking at this, that there's no way that subtracting 2t squared is going to subtract everything and get 0. So this is not 0, that again, linearly independent. So let's do one more of these. So our, I don't want to do anything too complicated here. I'm going to show you how this kind of works out. I'm going to do ones that are really obvious. T squared. And how about 4t squared? And let's see if these are linearly independent. And hopefully it should be obvious that they're not. They really are the same function, just with a different constant out in front. That makes them non-different because the base function is not different. But let me just kind of show you exactly how this works with these constants. So we would put a c1 out in front of t squared. We'd put a c2 out in front of 4t squared. We'd set that equal to 0. And then if we make c1 4 and c2 1, then that gives us a linear, oh, I'm sorry, I need to make one of those negative, right? And how about c2 being negative 1? Then that would make this equation equal 0. So that would make, we'd have 4 times y1 minus y2 equal to 0. Right? And this is called the linear relation. So if we want to find a linear relation between them, that basically means just find the constants that will then make it 0, and the constants that are not 0 that make it 0. As far as the Wronskian goes, we'd put t squared in the first one, we'd put 4t squared in the second column, take the derivatives in the second row, 8t. Then we multiply down diagonally, and that would give us an 8t cubed, and then we subtract when we multiply up. 2 times 4 is 8, t times t squared is t cubed, and sure enough we get 0. So the answer too, is this linearly independent? The answer is no, and if the answer is no, it does have this linear relation. All right, right, let's do another example, but this time with putting together solutions. So the first part of this, let's verify that e to the 2x, well, let's do another one, and x e to the 2x, pause. So we want to show that e to the 2x, x e to the 2x form a fundamental set of solutions. Fundamental set of solutions. And those are going to be solutions to y double prime minus 4y prime plus 4y equals 0. All right, now to form a fundamental set, there needs to be two different things that happen. So actually, let me call this part A so I can do the two different things that need to happen. First of all, we need to show that these two are solutions. Show that they're solutions. And to show that they're solutions, if you remember back to the beginning, or if you remember back to the exam on how you checked your answer, you just plugged those into the differential equation. So that means that when, we'll call it y1 is e to the 2x, we're going to need its first derivative, so that would be 2e to the 2x, and we're going to need its second derivative to plug into that differential equation, so that would be 4e to the 2x. Now if we plug that into the differential equation, we get the second derivative, so that is 4e to the 2x minus 4 times 2e to the 2x, that was the first derivative, plus 4 times e to the 2x, and let's check, we've got a minus 8, a plus 4, and a plus 4, and sure enough those all cancel and we get 0. So that means that e to the 2x is a solution. Now we need to do this for that second function, the x e to the 2x. So we need its first derivative, which we need a product rule for. So the product rule, derivative of x is 1, and we have e to the 2x, plus derivative of e to the 2x puts a 2 out in front. And then a second derivative of e to the 2x is 2e to the 2x. Another product rule, so we're going to have a 2e to the 2x plus e to the 2x, that derivative of that is 4, or 2, and 2 times 2 is 4, 4x e to the 2x. And then let's plug all these in. So the second derivative, I'm going to combine those first two terms for the second derivative. 4e to the 2x plus 4x e to the 2x, that's the second derivative, minus 4 times the first derivative, e to the 2x plus 2x e to the 2x, plus 4 times the function x e to the 2x. All right, let's see if all this stuff cancels. So we have a 4e to the 2x and a minus 4e to the 2x. Okay, so those guys will cancel. Then we've got a minus 8x e to the 2x and a 4 and a 4. So yes, all of those cancel, and sure enough we get 0. So that means that x e to the 2x is a solution. So both are solutions, and then we had to see if they are linearly independent. Are they linearly independent? So I'm going to use the first method. You can use the Wronskian if you want to. The first method, put constants out in front of those functions, plus c2x e to the 2x. Set it equal to 0. And then if you look at the constants out in front of like functions, e to the 2x is different from x e to the 2x. So really those are just the constants out in front of e to the 2x. That constant has to equal 0. And the constant out in front of x e to the 2x has to equal 0. So are they linearly independent? Yes. So what we've done here is we have now verified that they form a fundamental set of solutions. So now for the second question, I'm going to ask, what is the solution, and this is a general solution, to y double prime minus 4y prime plus 4y equal to 0. So the answer to that would be that we would take these, did I just use x's? I did. Man, I always confuse whether I'm using x or t for my independent. Okay, so the solution is going to be y of x, and we are going to take a constant, multiply it by each of the functions in our fundamental set of solutions. C1 e to the 2x plus C2x e to the 2x. And there's our general solution to that differential equation. All right, so I'm going to continue on with this example. And I am going to give you that given that y sub p of 1 is equal to x squared e to the 2x, and I'm going to tell you that this is a solution to y double prime minus 4y prime plus 4y equal to 2e to the 2x, and that y sub p of 2, which is equal to x minus 2, is a solution to y double prime minus 4y prime plus 4y equal to 4x minus 12. Now I'm going to give you that those are solutions to those, but you could check them. You could just take two different derivatives, plug them in, and see that they work. So my next question is going to be to find, so this is what, a part C. So let's find a solution to y double prime minus 4y prime plus 4y equal to 2e to the 2x plus 4x minus 12. Actually, I want to change that, just to make this a little bit more challenging. Let's make it 12x minus 36. Okay, so solutions to these, if you look back to what we did, we used superposition to take the fundamental set of solutions first. So that was the general solution that we got from part B. So that was C1 e to the 2x plus C2x e to the 2x. So we got that from part B. And then we start adding on all these particular solutions that go with the different differential equations, so the different non-homogeneous parts. So notice that this guy goes with 2e to the 2x, so we would add on that guy, x squared e to the 2x, plus now we've got an x minus 2 going with 4x minus 12, and notice that what we have here is 3 times 4x minus 12. And so what we would add on for that part is 3 times that solution to that non-homogeneous differential equation. And that would be our solution to this guy. Okay, so once again in summary, we take the general solution from the fundamental set of solutions and we put constants out in front. And then we start adding on a function for every single function that we have on the right-hand side of our differential equation. So function on the right-hand side of our differential equation, solution that goes with that. Function on the right-hand side of our equation, solution that goes with that. And in fact, 12x, that's a function on the right-hand side. 3x, that's the solution to that part of it. And so our final solution just adds all those together.